Okay, up now we have Shinji Sumimoto. He's a senior architect and director of the Software Development Division of Next Generation Technical Computing Unit at Fujitsu.
Firstly, I appreciate that I have a presentation here. I'm very thanks to the organizing committee. So today I'm talking about overview of Fujitsu Lustre-based file system. Yeah. And here's my outline of this talk. Okay. And first talk about target system overview, and then I talk about goals of Fujitsu cluster file system, such as FEFS. I also present about our system architecture, and then about our file system overview. So let's talk about target file system, K computers. And RIKEN and Fujitsu are now jointly developing the K computers. Will be included at the RIKEN AICS Advanced Institute of Computational Science in Kobe by 2012. So for the target system, Fujitsu is now developing a cluster file system called FEFS for K computers. And here is a miniature system model of K computers. And here's a picture of the first 8 racks of K computers. This is a Japanese character K. That means the first character is Kyoto. This character also means Japanese unit number. That also means 10 peta. This is Japanese 10 peta means 1K computer. So the RIKEN names the K computer. And here is the system configuration of the K computers. And here is the computing nodes. It's over about 80,000 nodes. And here is almost some torus mesh network. And here is the local file system storage. And here is global file system and content servers. Here is connected by a global network. This is networks in Infinity. And here are servers in the control, system control, and maybe management servers as Job-IO. And user can log into through the internet to the front-end servers and access the global file system and dispatch jobs to the whole computing nodes. And here is the architecture of computing nodes. And zero architecture computing nodes is over 80,000 nodes. And this is a node configuration. Here's 8 core processors and shared electric cache and memories. And peak performance is over 1 petaflops. And memory is around over 1 petabyte. And this processor is based on Spark, and I'll talk about later. And the interconnect is logically 3-dimensional for this network. And the peak bandwidth is one link is 5 GB per second, the bisectional for each 3-dimensional spot. So total bisection bandwidth is over 30 terabytes per second. And this is the operating system, Linux on Spark. And here is the CPU features of K computers. It includes 8 cores processors and 2 simultaneous operation units. And it's a 2 multiplier at floating point unit and executing the simultaneous instructions. And we also have some extensions to Spark architecture. For example, we have 256 floating registers. And this also processor has also a shared 6 megabyte electric cache. And it also has a variable of the internal core. And also a sector cache such as that. The performance is 16 gigaflops per single core, and total one CPU is 128 gigaflops at about 58 watts. And here's our target system. So I talk about the goal of our file system in the FEFS. FEFS means Fujitsu Exabyte File System for peta and exa-scale supercomputer we achieved. These are 3 topics. One is extremely large, and 100 petabytes, 1 exabyte. And second, massive number of client servers. Second point is high performance. Throughput of single stream and parallel IOs. And also reducing file open latency and avoidance of interferencing among jobs. Third one is, of course, the file system must have a high reliability and high availability. So always contain file service when any part of the file system will be broken part. So our file system is optimized for these features. So let's talk about the design challenge of our file system for the computers. There's 4 topics. First one is how should we realize high speed and redundancy together? For example, we focus the redundancy and reliability, the performance will go down. So there is a trade-off. Second point is how do we realize ultra high scalability over 1,000 servers and accessed by over 100,000 of computing nodes. Third point is how do we avoid I/O conflict between jobs? For jobs, 3 services should be occupied for each job. In comparison to user usage, I/O operation by multiple users and multi jobs, how do we realize that? The fourth point is how do we keep robustness and data integrity? This should be an eliminated single point of failures. We believe that we are investigating to realize these challenges. We have introduced an integrated cluster file system, layered file system. Maybe this is actually presented by in the morning presentation, almost same policies. So we divided into 2 file systems, and local and global. And the local file system is optimized for the high performance. And here's the computations, and high speed, and dedicated, and temporary use. And second file system, global file system. This is optimized for high capacity and redundancy, and shared by multiple servers and other classes in the user jobs. To realize the 2 file systems together, we introduce staging. This is staging process is controlled by the job scheduler. When you user dispatch jobs, this staging process is automatically stage in and stage out. This is our file system architecture. And let's talk about file I/O architecture of K computer. Our file system is optimized for the hardware architectures. This is optimized for scale of file operations. And this achieves the scalable storage volume and performance, but also eliminating I/O conflict and every component. Basic policy is a job. This is maybe a K computer architectures. This is X, Y, and Z horizontal, vertical Z axis. The jobs for this kind of system should be I/O straight down this node. For example, this here. This is maybe a I/O node, and this is computing node. The job here is processing I/O through the vertical I/O storage. So to realize this job scheduling, allocate the jobs and allocate the storage. It's I/O drawing technology for a local file system. So we assume that this type of I/O case usage. For a local file system, we assume that the parallel I/O and single stream I/O and master slave I/O. And in a global file system, is maybe a huge number of variety of file access. For example, I/O nodes and compute nodes, or other HP system and login nodes. So let's talk about our file system overview. Our file system is based on currently 1.8.1.1 based, and optimized for I/O system architectures. So, for example, integrated layer cluster file system and drawing out of hardware performance and reliability. And our file system main features is Selectable and ultra high file I/O and MPI-IO performance, and low time impact on the job scheduling of our file I/O. And third point is huge file capacity, and also high reliability and usability, and dedicated resource allocation to provide the intervention among jobs. To realize our features, we extended the current Lustre architectures. Here is a summary of several functions are extended for our requirements. Our main target is a large-scale file system and performance availability. And here is maybe for a large-scale file system, file size and the number of files, number of OSs, etc., are very expanded. And we also have performance and local file system and distribution. And also we are in a global file system, QoS schedule for users supported. And here's our requirement of our file system or Lustre extension. And this is a system limits and no scalability, and block size by electric scale FS. And current Lustre is like here, but our goal is here. For basically max file system size up to 100 petabyte, and the file size also extended to 1 petabyte, and also OST size also, and also we have stripe count to 160 to 10K, such kind of that. And also I extended to the number of OSs to 10K or such kind of that. And we also extended the block size of electric scale FS. And we also, our architecture is Spark, that is big endian. So we also support IA, and so big endian support and endian conversion is also implemented. And directive quarter and infinite bonding and QoS are implemented. So let's talk about our technical issues. I can point at the four. One is the MDS and OS scalability, second is I/O zoning, and third one is OS QoS, and fourth one is staging, and other topics. First, I talk about MDS and OS scalability. To realize the scalability, locality is very important for. So our strategy is utilizing this locality as much as possible. For example, MDS scalability, maybe a dividing file system. And second, there's a cluster of MDS basically needs future Lustre 2.8 space. Second, OS scalability of 1,000 servers. So you have 3 points, minimizing OS server response. Second, avoiding interconnect congestion. Third one is minimize storage response. This is very important. Second point is I/O zoning. This is what someone said in a previous presentation. Issue is sharing disk volume network links among jobs cause I/O performance degradation because they are conflict. For example, there are two jobs and share the job A files like here and job B like here, and access their conflict on the I/O file. This will cause a performance degradation situation. And our approach is job is allocated to this, and also storage is allocated this. So in that case, there's no conflict. And also divide into interconnect and storage. That is our approach. Third point, and we introduced Selectable Policy Qos. And in our system, system manager is able to select Share QoS and best able to QoS. I talk about the first one. And in the Share QoS, this is avoiding from someone occupying a file I/O service. Without Share QoS, when a single user case, user A processing make a huge I/O and occupy the I/O bandwidth. But that is okay because single user. But in the much user cases, user A also a much huge I/O, so user B is very, very small, and but I/O response. That's not fair. So with fair Share QoS, the QoS limits the maximum I/O usage rate. So user A is limited limited I/O rate like this. In a much user case, there's the same I/O bandwidth are allocated. This is file here. And here they also support best effort QoS. Best effort QoS is same as fair share, but a single user can use as much as possible. One thing client, a user can occupy and hold the I/O bandwidth, but two users sharing divine too. Here's a single I/O server case, and here's a much other case. So our system can support the two types of QoS. Next topic is the staging, system control file transfer. The staging goal is minimizing I/O conflict by controlling copying speed and I/O timing. Here is staging from the global file system to local file system. The stage out means from local file system to global file system. And the user that use our system and specify the files and stage in and stage out. For example, using a directive. For example, transferring an A.4 file to rank 0-15 nodes like this. These are computer-specific directives. And so our system is staging timing is we are pre-staging procedure controlled by job scheduler. And also stage out is processed during job execution. And here's 3 jobs, and here's timeline. First one is job dispatched, staging, and job execution, and stage out. The second one is also like this, staging, staging, and job execution out. Such kind of automatically staging styles process controlled by the job schedulers. And next topic is high reliability and high availability. Issue is about keeping system reliability and availability against failures. And our approach is a basic style and full-duplex hardware architecture, and running against a single point of failure. So duplex passes of infinite band and a pipe channel and I/O server are data robustness using the radio disks. And also the server the communication links are dynamically switched against their failure by software. So files is not stop such kind of failure and maintenance. The other topics are relative thinking, and first is kernel independent servers and MDS OSs, because we support such a Red Hat and such kind of does not change the kernel. So patchless and kernel independent server is very, very needed. And current implementation depends on the kernel source code, especially EX file system. That's the problem. And second issue is LNet and OSS MDS setting, configuration setting for 100,000 of client servers. So because this is automatic configuration is needed, and also needed for checking connectivity among servers, because ping, LA ping is okay or not, such kind of that. Third issue is data integrity. because file FSK is for data impractical for over petabyte with the file system. These are our issues. So let's show some experiment evaluation result on FEFS. And this is a preliminary, and this shows that this is worked. And here's our IOR result. This is a result of 288 OSS and 864 OSTs and 10,000 clients result. And this requires maybe a POSIX write is around 96 gigabit per second and read 148 gigabit per second. And second result is a QoS result in the PC clusters. This is a case of user A is 19 node job and user B is a 1 node job. And each node repeats create files and remove files of 10,000 files. And this is the result. This is a single user without QoS, like here. It takes about 4 seconds to create 10,000 files. And also 4.2 seconds for removing 10,000 files. However, in a multi-users, like that. So, and the time of the user B is around take up the 10.1 seconds. And remove file also 15 seconds. This is not so fair. So when we introducing QoS, the result is creating files around 3.9 seconds and removing files 5.5 seconds. This is almost a similar result of the single user. So QoS is well take effect. And here I am present summary and future works. And we described of FEFS, Fujitsu's Lustre-based file system for the K computers, developed by RIKEN and Fujitsu. And currently we are testing and RIKEN QoS system against the daily earthquake and blackout problem in Japan. And this take about high-speed file I/O and MPI-IO and huge file capacity and scalability capacity and speed by adding hardware. It also takes a higher reliability and usability. And future works, and we are currently based on a 1.8.1, but revised to the newer version of Lustre, maybe 1.85 this year, and I hope next year at 0.1 based. That's thank you for my presence.
The Lustre extensions that you're doing seem to match fairly closely with the Lustre on ZFS project. Have you guys looked at that at all and seen if there's anything you could leverage from their project?
Your question is how do we using ZFS?
Yeah, whether or not you can use anything from the Lustre on ZFS project to help with your file system extensions.
Currently, it's extended by exe maybe 4 base. Okay. Yes, I expanded something. Yes.
Are your Lustre servers running on your I/O nodes?
Yes.
Are the Lustre servers running on the I/O nodes?
Yes. Maybe Lustre client is a computing nodes, and I know the Lustre servers. Yes.
So they're servers, not routers.
Yes, the server is also Linux.
Okay. And then how long, you're saying that you dynamically assign jobs to specific sets of I/O nodes. How long does a job live for that special part of the file system?
This time, dispatch time. Maybe
You had a slide where you showed the contention, and you were able to assign specific servers to a job.
Yes. Maybe our job schedule scheduling for maybe 1 hour, a long period of scheduling. So the schedule down in until the previous job finished. Then it takes soon.
So that's some very interesting work you guys have been doing. I just have one question for you. When can the community expect to maybe see some source code?
Maybe we have scheduled because this is a GPL code. So currently we have dedicated users. So maybe when we can distribute our code, but you cannot run because currently very specific for our hardware something. Because this kind of feature is a Spark Linux, such kind of like that. So maybe in the future, we would like to compete with our experience and code to the community. And in our future, we want to debase the future Rust based, but our extension is far so we are already discussing the Sun and Oracle, but the roadmap and our requirements are here. But in that case, in the near future, is this here. So in that case, this point is maybe our contribution to the committee. This is the point, I think.
Okay, I think we're about out of time. One more? Anyone?
With that file system size, in case of a power outage, are you protected against power outage for your backend disk system and thousands of OSs? And if that's the case, how much of a cost fraction did it take?
Sorry, could you repeat?
I'm wondering whether your file system infrastructure is protected in case of a power outage. I mean, if you are dealing with thousands of OSs and roughly...
Okay. Yeah, that's your question is maybe 10K OSS is a very challenging area. So we are trying to increase OSS. How do we reach the work and try and try and tuning? This is right now we are doing.